Hello, this is Alex Voss, your professor in TVE course, and I want to welcome you to our section on transistors. And what a better place to do it than where I am right now, the campus of Texas Instruments. Texas Instruments is one of the largest manufacturers of semiconductor products in the world and premier in the development of semiconductor and transistor technology. They started transistor technology production back in the 1950s, and they're well known worldwide for their influence on semiconductor and transistor technology. Well, let's begin our course and have fun learning about transistors. And that is the picture of the very first Walter Brattain built transistor. And just to give you a little more idea, we're going over the construction of the bipolar transistor again, even though I talked about it earlier. We have an emitter, we have an N region doped, a P region doped, and an N region doped, making the three connections. Now, we talked about, one thing I like to think about a transistor is thinking about it as two diodes. Now, the thing about a transistor is you can't just stick two diodes together and make a transistor, because there's a magic that occurs with the way the dopants are used and the size of the regions to allow the amplification to happen. But when you're testing a transistor, you can think of it as two diodes. Right now, I've got two diodes here, and they're connected with a collector, and here's a diode, here's a base, and here's a diode, and here's an emitter. And it would match up with this transistor over here. And the neat thing about that is, if I want to determine if a transistor is good or not, I can take a standard ohm meter and I can measure from the base to the collector and from the base to the emitter, and then reverse the bias. You know, if I use a multimeter and or a battery resistor, an LED tester, I can check each pair of leads from the base of the collector and the base of the emitter, and if I reverse the bias, you should see conduction in one direction, which means it would have a low resistance on the ohm meter, and then if I reversed it, conduction or the resistance would be high, and so I'd have a high resistant reading on the ohm meter. And so when I see a difference in an ohmic value reading from an ohm meter between the base and collector when the polarities are reversed, and when I see a difference between the ohmic value reading between the base and the emitter when the polarities are reversed on a transistor, that is an indication that it's a good transistor. I've seen a lot of transistors where I measure, and you'll see a good, like from the base to the collector, and then you measure the other side and it's either dead short or it's wide open, infinite resistance, then that's a bad transistor. You know, each junction acts like a diode, and you know the way you test a diode is you take a diode and you measure it one direction and it shows a high resistance. You measure it the other direction and it shows a low resistance, and that tells you it's a good diode. If it acts like a total short or a total infinite resistance open, then you know that it's a bad diode. Same thing for a transistor, because a transistor can be measured as if it is two diodes. And so lots of times when I want to determine if a transistor is good or not, I'll just pull out my ohm meter and I will check that. Again, just to go over it again, here's another drawing that shows a transistor as the schematic symbol. Here's a transistor as a schematic symbol. Here's a transistor as a drawing showing the actual construction of the silicon or germanium. And here's the same transistor shown as two diodes. An N-doped semiconductor, now the dopants, when you talk about dope regions, an N-doped semiconductor material has a majority of electrons and a minority of holes. Now what's a hole? Okay, now when you talk about a atom, okay, now an atom and some atoms have what they call loose electrons, which means in the outer valence shell of the atom you can lose an electron that goes off into space because it's attracted by a positive electric field or something that makes it leave the atom. And so when that has left that atom, that makes a hole. So that makes the atom more positive than it was before. So when I have an excess of electrons in a doped region, that would be considered an N-type doped region. If I have a majority of holes, which means it's more positive, that would be a P-type doped region. So we're actually setting up electrical biases by doping a material. Now, here's where the magic occurs with the transistor, and I'm going to try to make it as simple as possible here, but I want you to pay attention closely, because this is where it all comes together if you want to understand how a transistor works. Okay, here we have a transistor, an N-type region, P-type region, and an N-type region. This is an N-P-N transistor. This is the emitter region, this is the base region, this is the collector region. For a transistor to work, you must have proper bias between the emitter, base, and collector. Okay? Now, we have a battery here called VBE, and VBE stands for the voltage applied between the base and the emitter. And so here's the base, here's the emitter, and this battery is applying a voltage between the base and the emitter. We have a higher, the more plates on the battery represents usually a higher voltage. So we have a higher voltage battery here. We're going to call that VCB, which means the battery or the voltage applied between the collector and the base. VCB, voltage collector base. VBE, voltage base emitter. Okay, these two batteries are providing us with the proper bias for this transistor to work. The VBE battery causes the emitter base junction to forward bias. Okay, what does that mean? When we have no voltage applied to this transistor, we actually have a reverse bias between the p-n junctions on both sides of the base because of the dopants. And that makes something called a depletion region, which is an area where nothing's happening, where there's no charge. And the depletion region is sort of the demilitarized zone between two areas, if you want to call it that. And that's what basically keeps the transistor from conducting. Now, if I apply a voltage negative to the emitter, positive to the base, what that's going to do is that's going to overcome the inherent bias in the transistor between this junction. Okay? So the VBE voltage causes the emitter base junction to forward bias. Now when a junction is forward biased, that means electrons start to flow. The silicon transistor has to have a 0.7 volt forward bias for conduction. A germanium transistor has to have 0.3 volts for conduction. So we're saying this battery is putting out something higher than 0.7 volts. And so that higher than 0.7 volts between here and here causes conduction. Okay? Electron current flows from the emitter to the base, filling the holes in the base. Okay? So we forward bias this junction and we're causing the electrons to spill from the emitter into the base. What happens when I start filling a region with electrons? Now this was a positive doped region, but when I go into conduction, because I made a positive here from this battery and a negative here from this battery, and it started a current flow, I'm actually injecting electrons into the base from the emitter. That has eliminated this depletion region, and it's caused us to go into forward bias, so we have conduction. So this base is going to start filling up with holes. Electron current flows from the emitter to the base, filling holes in the base and creating a negative charge in the base. Now, this battery here, this region here naturally is still reversed by a reverse bias junction. Okay? But because of the different dopants, the size of the regions, and all kinds of magic they do when they build a transistor, filling up the base actually causes the electrons to saturate the base, and they're spilling over. They're like a pack of wild lemmings running over a cliff falling into the collector. And that's when the magic of amplification occurs. Okay, so electron current flows from the emitter to the base, filling the holes and creating a negative charge on the base. The VCB battery, the battery applying the voltage between the base and the collector, causes a reverse bias on the collector base junction. It makes this go to a high resistance. However, because of the proportion of the dopants and the individual regions, the negatively charged base has a high positive voltage applied to the collector and a narrow width. Okay, let me get this. Let me go over this where it's really clear. When these dopants are different, okay, when the proportion of dopants in the individual regions and a narrow width of the base region, the base electrons flow into the collector like they're falling down a hill once we start this conduction. Okay? And the electrons are pushed through the two depletion regions here and here, and the current and the voltage in the transistor would follow the rules of Kirchhoff's and Norton's laws. So what I'm saying is, once we start this conduction here, it will actually cause a conduction over here. Okay? And the size of the voltage here determines the size of the current flow here, from here. And so what would happen is a varying current, a varying voltage on this base would cause a large current flow through the whole transistor. Okay? This base acts like a gate or a valve that allows the current to flow. Okay? We have the injected electrons that come in the emitter. We have the collected electrons which go to the collector. And these electrons, oh by the way, diffusing electrons are what you create when you create conduction into the base. So the bias on this base junction here, right here, is going to control the amount of electrons flowing through. And this voltage is going to determine the total flow through the whole system. So a little voltage here can cause a large current flow here, creating a large voltage change over here. And so this is basically the way that transistor works. And so, you know, if we were to stick two diodes together, it wouldn't work because they have fixed depletion regions and fixed dopants, and they're just designed to turn on or turn off. But we have varying levels of dopants between these three regions. So basically, when we get the junction between the emitter and the base forward biased, then it's going to fill up the base and allow conduction even across reverse bias junction into the collector. And that's where that magic starts to occur, where you're going to get amplification in a transistor. And so, yes, when it's simple, you think of NPN dopants, but it's also the degree of dopants, the spacing between the base and the emitter, and all of that stuff goes to make a system where a small bias at this point can control a large current flow through here. And whenever this bias changes, there's a proportional change in the current flow. And so we have nice clean current flow change when we take this across a dropping resistor over here on this end. We drop a voltage across that resistor. We're going to see a nice clean voltage change when we have a voltage change on the input to the base, except this voltage change is small and this voltage change is large, but the voltage change on this output here is proportional to the voltage change that's applied to the base.
Is it positive?